Hey, today we're going to talk about description and correlation. Super fun stuff, super exciting. I accidentally drew on the thing, so you're just going to see me scribble. Oopsie doopsies. Sometimes you make mistakes when you're recording, but if I stall, it will go away. Um, so, yeah, description is how we describe sets of data, right? In order to understand how the data is behaving. There are lots of ways to describe data. We can do it with graphs. We could do it with very simple descriptive statistics, some of which you are probably already familiar with. And then there's correlation. We've talked about correlation before when we looked at positive, negative relationships between variables. So we're just going to go a little bit more in depth with that. So just to review, there are 4 scales of measurement. These are going to come in handy soon. So remember I mentioned that these were going to be important. They're back. So we have 4: nominal, ordinal, interval, and ratio, right? Nominal is categorical. Ordinal introduces magnitude. So this is greater or less than this. Then we have interval scales, which have equal intervals between each measurement. And then we have ratio, which has a true zero, meaning zero actually means a complete absence of something, right? So and a great example of this would be the temperature. If I asked you, is the current temperature comfortable or uncomfortable, that would be nominal, right? If I said, is this hot, average, or cold, that would be ordinal, right? As I go down, I'm decreasing in temperature. Then we have interval, which has equal intervals, which are temperature measures like degrees Celsius and degrees Fahrenheit. But there's no true zero because zero does not mean the complete absence of temperature or heat. And then we finally have ratio, which would be the true zero of the Kelvin scale, where if you're at 0 Kelvin, then that means that there is no heat. So in our next video, we're going to talk about inferential statistics. Today, we're talking about descriptive statistics, but I want to talk about both so you understand the difference between them. Descriptive statistics are talking about what is actually happening in the sample. So if I get a group of 30 people that are college students, right? I might take those 30 people and give them some survey, and using descriptive statistics, I can describe what is happening with those 30 people. I can determine how they behave on average. I can figure out their average height. I can see like what the range of levels of anxiety between them are, but I can't apply that to the outside world using descriptive statistics. So just because 70% of the people in my study have high anxiety, it doesn't necessarily mean that 70% of people in the real world have high anxiety. That's where we're using inferential statistics, where we're taking information from our sample and then applying it to the population. By the way, if you notice the weird thing going on with my fonts, is that the word I'm looking for? Not fonts, not kerning, where sometimes my words are just a letter is hanging off them. When I uploaded the PowerPoint, it's doing this weird thing, and I just don't have time to fix it right now. So enjoy the fact that sometimes words are just going to be cut off mid-word. So now that I've admitted to my human flaws, I would like to talk about different types of charts. Charts and graphs are really great. Get out of here, cat. Get out of here. Nobody wants you. So the charts and graphs are a really great way of showing how data is behaving. Just so you know, while I'm talking, I'm holding a cat in my arms like a little bitty baby because he's a little bitty baby cat. You're a little bitty baby cat. All right, on to the graphs. So you're probably familiar with the pie chart. The pie chart is a great way to, at a glance, see relative percentages of things. So right here we have ethnic breakdown of a specific group. So very clearly we can see that 45.4% of the group is Hispanic. There are very small chunks that are American Indian or indigenous or other, right? So it's a great way of just seeing at a glance what the relative percentages are. One fun thing to think about is the ethnic backgrounds. That is a nominal category. The percentages is a ratio scale, right? So a pie chart allows you to look at the relationship between a independent variable that is nominal, categorical, and a dependent variable, in this case, percentages, which is ratio. Bar charts do almost exactly the same thing as pie charts. So we can look at the relative percentages or numbers of something for categorical data, right? So we have our independent variable, which is the month of the year, and we have our dependent variable, the number of students who were born in that specific month. So we can very quickly at a glance see, ooh, a lot of people were born in June. Not very many people were born in August. Right. So bar charts and pie charts are a great way of working with a nominal independent variable. Okay, we also have frequency polygons. If you'll notice, our independent variable is no longer nominal. It's height in inches. I'll give you a chance to think about what that could be: nominal, ordinal, interval, or ratio. Height in inches would be ratio. Hopefully that's what you said. If not, please study more. And our our dependent variable is the frequency, the number of players. So as you can see, right, there are very few short players, right? 69, haha, nice, is the shortest that we have. We don't have anyone who's 66 inches, and 87 inches is the tallest that we have. But right about in the middle, right, the average height seems to be like around 78, 81. The most frequently occurring height is 78 inches. So our frequency policy allows us to kind of at a glance just see where the overall shape of the data, where the data is going, where the peaks are, and how the data is behaving overall. Sometimes you might want to use a histogram or a histograms, or maybe it's a histograph with a master's of science in some field like biology or something. So sometimes you want to see the frequency of a specific distribution. I'm not sure if you can see the x-axis, but this is measuring annual salaries. So as you can see, there are a lot of people who are on the lower end of the salary scale. You have a few people there are 32 people who are making $76,000 a year. You have 9 people who are making 104,000, and then as you go up, you see those salaries increasing. But a lot of people are in that very low range. So, because the way that you can tell the difference between a bar chart and a histogram is the fact that a bar chart, the bars don't touch. And that is because in a bar chart, you're looking at separate data, right? If I'm looking to see how many people like chocolate versus vanilla versus strawberry ice cream, those are all different flavors. So they're kept separately. They're nominal, they're categorical. When you're looking at ratio data, we know that there's information in between there. So the fact that the bars are touching represents the fact that the data is continuous. So if you were looking at a histogram and a bar chart and you weren't actually sure which one you were looking at, now you'll know if the bars are touching, it is a histogram. If the bars are not touching, it is a bar chart. And histograms, as well as frequency polygons, give you the same type of information. So it's up to you to decide if you prefer to use a frequency polygon or a histogram. And then you'll remember the scatter plot TS, or as some kids call it, a scatter plot. And the scatter plot takes a lot of individual bits of information, and what we can use is what's called a regression line to represent that information. So the regression line is related to the Pearson R, which is also called the Pearson product moment correlation coefficient. It's also called the least mean squares regression line. There are lots of names for this line, but essentially what it's doing is it's taking all this data that is doing whatever it is and just going, okay, this is what the data looks like, but on average, what's the data doing? Is it increasing, meaning that is there an increase in the slope, meaning that there's a positive correlation? Is the data in general decreasing? Is there a decrease in the slope, meaning a negative correlation? Or is there really no correlation between it? It does kind of whatever it wants, meaning there's no correlation between the data, right? So just to remind you, we have the positive correlation, R equals +1. We have the negative correlation, R equals -1. And then we have no correlation, R equals 0. Some of you probably went, but Professor Thompson, what about the curvilinear relationship? Yes, our old friend, the curvilinear relationship. And with the curvilinear relationship, if you remember, right, with these data sets we're looking at a R that also equals 0. And the reason for that is because the linear relation, the linear regression is going to treat it as one line. But if you were to make that line that I just did, right, the actual line, because a curvilinear relationship isn't a line, right? This is not a line. If you remember geometry, that's not what a line looks like. So the line that best represents that data is a flat horizontal line, meaning the R equals 0. But we know that there is a relationship, right? The data is behaving in a specific way. It's not a linear relationship, but it is a relationship. So if you think you have a curvilinear relationship and you're getting an R that's close to 0, what you can do is what's called restriction of the range. So what I can do is I can measure the data up to one point, right? So I could look at this side of the data, and I could look at this side. I just realized that you can't see me pointing. You can't see me pointing to the thing. But I could look at the left side and the right side of the data. I had to redraw this line because I'm just so funny. Man, I wish you guys were here. I'm having so much fun by myself with my cat. So if I look on this side, then I have an R of +1. If I look at this side, right, get back here, line, then I have an R of -1. So by restricting the range, I can see that there actually is a curvilinear relationship. So one thing to know is that usually when you see an R that equals 0 or an R that is close to 0, that means that there is no relationship between the two variables. Now, it could mean that there's no relationship between the variables, or it could mean that you have a curvilinear relationship. So the first thing that you'd want to do is look at the old scatter plot, right? And you might start to see that the data is behaving in a certain way. But the only way to be sure about that is to restrict the range and then compare this side over here and get a little Pearson R. Then you look at this side over here. That's the sloppy circle, and you look at that Pearson R, and then you'll know for sure if there's a curvilinear relationship. Okay, so effect size is the percent of changes in one variable that is caused by another variable. So let's say that the R value for the relationship between alcohol and getting drunk is 0.90, positive 0.90. That's a very strong value of R. Now, the question that you are asking right now, because I know you, is what percent of your intoxication is determined by how much alcohol you've drank, right? So I would say, well, you have the R value, so let's find the R squared. 0.90 squared is 0.81, right? So that means that 81%, 0.81, 81% of your intoxication is determined by how much you've had to drink. We know that there are other factors, how much you've had to eat, what you're drinking, the alcohol content, et cetera, et cetera, et cetera. So that's effect size. Now, just as a reminder, for the Pearson R, the closer a number is to 1 or -1, the stronger the Pearson R value is. The closer it is to 0, that means that it's a weaker Pearson R. But then for the R squared, because if you square a negative number, it's always going to be positive, R squared goes from 0 to 1. The closer it is to 1, the closer or the stronger the relationship is, right? So here are some examples. You'll notice that I made a little typo because this should be a negative right here. But if R squared is +1, if R is +1, then R squared is 1, meaning 100% of the change in one thing is determined by the change in the other. If R is -1, and I'll put that back there again. There we go. Oop. Just that's -1. That just trust me there, it's -1. So now it just looks like a weird sideways T. -1. You square that, you're going to get an R squared of 1. If R is 0, R squared is 0, meaning there's no determining the dependent variable based on the change in the independent variable. If R is 0.5, then R squared is 25%. If R is -0.75, R squared is 0.56, right? That's 56%. So if you ever want to know how to calculate R squared, then you just take your R and then you square it. And if you have R squared and you're wondering what your R is, you find the square root. It's that simple. So these descriptive statistics should be things that you are familiar with. So we have measures of central tendency, and we have measures of variability. Central tendency is telling you how a set of behavior behaves overall. So in general, what is this data doing? Variability tells you how much these scores vary from each other, right? So if there's an average score in my class of 70, right, you might imagine that that's because, well, some people got 90s, some people got 80s, some people got 70s and 60s and 50s, but it could be that everybody got a 70. That's an issue of variability. How much do the scores vary from one another? The idea that the average score is a 70 is an issue of central tendency. So just in case you don't remember from statistics, which I'm hoping you learned this in statistics. If not, I'm going to have to talk to your statistics professor. Give me their email. I'll make a strongly worded email. Uh, when we're talking about central tendency, we have mean, median, and mode. Mean is when you find all the sum of all of the numbers in a data set and divide it by the total number of numbers. So if I wanted to know what the mean score on your most recent test was, I would add all of your percentages divided by 37. I think that's how many are in the class. And that would be the mean. And I would get an average score of like 78 or something like that. The median score is the number that is in the middle. So you put all the numbers in order because if they are out of order, then that's not great. So you put them in, I almost said alphabetical order, numerical order from lowest to highest, and then you find the number that's exactly in the middle. Now, if there are two numbers in the middle, you don't have two medians. You just take the average, the mean of those two numbers in the middle, and that is your median. And then for the mode, you take the most frequently occurring number. So, for example, if 10 students got a 82% and that was the most frequently occurring grade, that would be the mode. Then with variability, we have standard deviation and variance. We're going to talk about those more later. For this class, you're not going to be calculating those by hand. You are welcome. So just be familiar with those terms. Variance, you can basically ignore for now. Standard deviation allows you used to help you determine how much. Great. I totally forgot to write the definition there. It's used to determine how much on average the data varies from itself. So for example, if I have a class that has an average of 70 and the standard deviation is 1, right, then the data isn't varying that much. I'm probably going to have a range of scores going from like 67 to 73 if the average was 70, right, with a standard deviation of 1. That's a very small level of variability. If I have a standard deviation of 10 and my average is 70, then I have scores ranging from like 40% to 100%. That's a lot of variability. And then range is the most simple way of measuring variability in a data set. You take the largest number and you subtract the smallest number. So if the highest grade in the class was 100 and the lowest was a 50, 100 minus 50 is 50. So I have a range of 50. So mean, median, and mode are all interchangeably used to represent the average. Most of the times when you talk about an average or hear about an average, we're talking about mean, but any of these can be used to represent the average. So depending on what you're trying to prove, you might choose to use one or the other. So for example, let's say there were 5 students in one class and 5 students in the other, and here is a distribution of grades between the two classes, right? Class 1 has 70, 70 and 80, and 80 and 90 and 100. Class 2, 65, 65, 90, 100, and 100. Which class did better, right? Now, if I want to say that both classes did equally well, all I could do is just point to the mean because both have a mean score of 84%. If you want to do the math real quick, you can go do that. Go click clack in your little calculators, right? Now, maybe I am the teacher of class 2. I want to show how superior class 2 is, right? So maybe I'll just report the median score, which is the number in the middle. Class 2 has a median of 90. Class 1 has a median of 80. Or maybe I'm trying to get more resources to a specific class, right? Class 2 hasn't gotten new computers. Class 1 just had a visit by a celebrity chef and they have like delicious snacks or something. And I'm like, we need more resources for class 2, so I'm going to report the modal score, right? On average, when we're talking about the mode, class 2 was underperforming comparing to class 1. And then just for fun, I'm showing you the range of both. Fun fact, I made a mistake here. That should be 35 because I changed these numbers at the last minute. I forgot to change the range. I'm human, but sometimes when you make a mistake, you still feel sad on the inside. Great, cool. Last thing that I want you guys to be aware of is what's called the regression equation. You may remember from high school or college math a little equation that says y equals mx plus b. The That is basically a linear equation, right? Now, the letters are changing slightly, but they all essentially mean the same thing. Y is your dependent variable, X is your independent variable, A is a constant. You don't really need to know that, but for you nerds out there, it tells you where the graph is going to go, so it moves it up and down. Then we have B, which is the value of R. It's very funny. You're thinking, why didn't they just put R? Don't worry about it. But that tells you the slope of your line. So is it going to be a positive upward slope or a negative downward slope? If B were 0 because your R were 0, then you would have a flat line. So that is your simple regression equation. Just be familiar with A, B, X, and Y, but obviously focus more on B, X, and Y. Now, one thing that you might not have known is we can include multiple variables. So if I wanted to include multiple variables, multiple independent variables specifically, and measure their effect on one dependent variable, then I would use the multiple regression equation. And you'll notice that each independent variable has its own value of R associated with it. And all these together determine what is going to happen in Y. So we have Y equals A plus B sub 1, X sub 1 plus B sub 2, X sub 2, our second independent variable. And we can go on and on and on until the end of time. Speaking of end of time, this is the end of this session. Yay, we did it. Go high five yourselves. You guys have done a spectacular job. And then once you high five yourself, wash your hands.